Dear audience, welcome to my presentation. The title of the presentation is Semantic Machine Learning for Manufacturing Monitoring at Bosch. This is a joint work of 4 authors affiliated with Karlsruhe Institute of Technology, University of Oslo, Bosch Corporate Research, and Bosch Center for Artificial Intelligence. Let me first introduce the big picture of Industry 4.0 at Bosch. Here, we develop and research an end-to-end intelligent solution where we start from the manufacturing plants, where the data sources originate, and go through the IT backbone where the data are collected, stored, and prepared, and reach the AI toolbox where machine learning modeling and semantic enhancement play an important role. Then we go back to the IT backbone and do the proof of concept and deploy the software system, and then reach the process and release the solution in the manufacturing plants. The goal of the solution is to improve quality and reduce cost. At Bosch, we have many use cases of machine learning activities. We have many data sources and formats, and when the data are collected, we need to negotiate and decide what tasks to solve. We have tasks for resistance spot welding, for hot staking, for ultrasonic metal welding, and for packaging, and many more. When the tasks are decided, then the data need to be prepared, machine learning models need to be developed, and the results need to be interpreted. At the end, the best model needs to be selected and deployed. Since we have so many use cases, it is very important that the machine learning methods should be generalizable and reusable. Let us focus on one use case, that is resistance spot welding, in which the welding machine connects to metal sheets using high current. The metal materials between the worksheets will melt and then congeal to form a welding spot to connect the metal sheets. This process is worldwide applied at the Bosch plants and Bosch's renowned customers. A car can have up to 6,000 welding spots. Just consider how many cars are produced every day. It is easy to estimate the economic impact of this process. However, process assurance is very challenging. The quality failure of one single spot can cause the entire production line to stop. This means the loss of time, several cars, and cost of maintenance. The quality monitoring task in this use case is to use the data to estimate or predict the quality indicator with the machine learning. However, there are many challenges in the machine learning activities. First challenge is transparency. We have many experts involved in the activities. They all have part of the knowledge of the data. For example, process experts have the knowledge of the physical process behind the data, and measurement experts have knowledge of how the data are measured. And data scientists have the knowledge of how to use the data to solve the task. The communication between them is very difficult because they all speak different technical languages, but it is also vitally important. Therefore, they all need to explain their knowledge and communicate transparently. The challenge 2 is data preparation. Since we have so many different data formats and data sources, if we need to develop machine learning methods for each of the source, it is extremely costly. Ideally, we want to transform all the data sources into one uniform data format. Then we can develop all the methods and the scripts based on this format. This will save cost greatly. Challenge 3 is the machine learning generalizability. Since if we have already developed the machine learning methods for one dataset, it is desired and necessary to transform the machine learning methods to other datasets, other data sources, and even other processes. Therefore, machine learning generalizability is very important. We propose to rely on semantic technologies as solutions to the challenges. The solutions have 3 parts: domain encoding, data annotation, and machine learning enhancement. First, let me give an overview of the solution. The core ontology encodes the general manufacturing knowledge in formal language. Then, Many domain ontologies are constructed based on the core ontology to encode the specific domain ontologies. The core ontology is connected with machine learning ontology, which encodes the general machine learning knowledge, and based on which the machine learning pipeline ontology can be constructed to encode the concrete machine learning solutions. This solution covers the activities from step 2 to step 6. Where the raw data are transformed to prepared data, and at the end, machine learning models, and the best model is selected from a series of models. Let us start with the first part of the solution, domain encoding, where the domain experts use the core ontology and templates. Templates are fragments of knowledge. Based on these two ontologies, the domain experts can construct the domain ontologies very conveniently, and the quality is guaranteed by the core ontology and templates. Since ontologies are unambiguous machine processable formal language, they are easier to understand for data scientists than the complex process descriptions. Based on the domain ontology, the domain experts can annotate the raw variables in the raw data with the domain terms and create a raw-to-domain mapping. This raw-to-domain mapping can be used for semantic enhanced ETL process to transform the raw data to prepared data with the domain ontology names. After that, the data scientists can link the core ontology with machine learning ontology and machine learning templates to create a machine learning solution and encode it to machine learning pipeline ontology, from which machine learning feature groups assigned to each feature variable in the prepared data, feature processing algorithms, and feature process groups can be automatically reasoned. This enables automatic construction of parameterized machine learning pipelines. The solution results in two modes. In the black mode, some machine learning pipelines are developed beforehand by data scientists. Then the domain experts only need to annotate the data and then select one pipeline from a catalog. In the white box mode, the domain experts, after some training of machine learning, can configure the machine learning pipelines using a graphic user interface. If they have been experienced with the GUI, then they can even construct their own machine learning pipelines. Let us go back to the use case and evaluate the machine learning methods. The task is estimation of the quality indicator. The y-axis is the estimated quality indicator, and the x-axis is the target. This figure shows that the correlation and the estimation correlates with the target very well. This gives us a subjective impression that the machine learning method works very well. To get a more objective understanding, we use the metric mean absolute percentage error, which is a relative error. And we see that for different machines, the semantic machine learning pipeline, in the semantic machine pipeline, different model is selected. For the machine 1, the best model is selected as a linear regression, and for the machine 2, the best model is selected as LSTM neural network. Let us conclude. Machine learning is a powerful approach that can provide good prediction accuracy for automated welding and also for manufacturing. Semantic enhancement improves adaptability of machine learning approaches by tackling the three challenges. In the future, we will investigate more machine learning methods, for example, feature learning, and more complex manufacturing machines. We also plan to integrate the machine learning pipelines into a new online welding control system and automation platform at Bosch. Thank you very much for your attention.